Imagine a universe without substance, a place where everything zips around at the speed of light. Nothing would stick together, no atoms, no stars, no planets, and certainly no us. This might have been our reality if not for a very special, almost ethereal something. Scientists call this something the Higgs field, and the particle associated with this field, the Higgs boson, has earned a rather dramatic nickname, the God particle. This nickname, coined by Nobel laureate Leon Lederman, was partly for marketing his book, but it stuck because it hints at the particle's fundamental role in giving mass to the universe. It suggests a power, a foundational importance that captured the public's imagination, even if many physicists prefer the less sensational term. The Higgs boson isn't some mystical entity dictating our fates from above. Instead, it's a fundamental particle, an excitation of the Higgs field. Think of this field like an invisible cosmic molasses, or perhaps a thick unseen syrup permeating all of space. As other fundamental particles try to move through this field, they encounter a kind of resistance, a stickiness. This interaction, this drag, is what we perceive as mass. Some particles, like photons, particles of light, don't interact with this field at all. That's why they are massless and can travel at the ultimate cosmic speed limit, the speed of light. Others interact strongly, becoming heavy and slow. The idea of an all-pervading field giving mass to particles was proposed in the 1960s by several physicists, including Peter Higgs. It was a brilliant theoretical solution to a major puzzle in particle physics. The existing theories, known as the Standard Model, describe the fundamental forces in particles beautifully. However, these theories initially predicted that all fundamental particles should be massless. This was clearly not the case. We knew electrons had mass, quarks had mass, and so did the W and Z bosons that carry the weak nuclear force. Something was missing, a piece of the puzzle that explained why some things have heft and others do not. This God particle nickname, while catchy, can be a bit misleading. It doesn't imply a divine intervention in the traditional sense. Rather, it underscores the particle's crucial, almost godlike power in shaping the universe as we know it. Without the Higgs mechanism, the universe would be a fundamentally different place. Electrons would not orbit atomic nuclei to form atoms because they wouldn't be bound. The weak nuclear force, responsible for processes like radioactive decay and nuclear fusion in the Sun, would behave very differently, likely preventing stars from shining as they do. So while the term might be a bit flamboyant, it does capture the profound importance of this tiny, elusive particle in the grand cosmic scheme. The theoretical prediction of the Higgs boson was one thing. Finding it was quite another. This particle was predicted to be incredibly elusive. It's not something you can just scoop up and examine. Producing a Higgs boson requires enormous amounts of energy, conditions similar to those just moments after the Big Bang. This meant scientists needed a machine powerful enough to recreate these extreme conditions, a colossal particle accelerator. The Large Hadron Collider, LHC, at CERN, near Geneva, Switzerland, was built precisely for this purpose, among others. It's a 27-kilometer ring of superconducting magnets designed to accelerate protons to near the speed of light before smashing them together. The search was a monumental undertaking involving thousands of scientists and engineers from around the world. For decades, physicists meticulously sifted through mountains of data from various experiments, hoping to catch a fleeting glimpse of the Higgs. The Higgs boson itself is highly unstable and decays into other, more familiar particles almost instantaneously after being created. Scientists, therefore, couldn't detect the Higgs directly. Instead, they had to look for the specific patterns of decay products, the ashes left behind after the Higgs disappears. It was like trying to identify a specific firework by examining the pattern of sparks it leaves in the sky long after the initial explosion has faded. Imagine sifting through billions of collision events, each producing a shower of particles, looking for a tiny statistical bump. This bump would represent a slight excess of certain decay patterns, hinting at the creation and decay of a new particle with a specific mass. The challenge was immense. It required incredibly precise detectors, sophisticated data analysis techniques, and an unwavering commitment from the global scientific community. The LHC experiments, Atlas and CMS were two gigantic independent detectors designed to perform these Herculean tasks. Their redundancy was crucial. If both experiments saw the same signal, it would lend much greater confidence to any discovery. Finally, on July 4, 2012, the moment arrived. Scientists at CERN announced to the world that they had observed a new particle with a mass around 125 gigaelectron volts, GeV. The characteristics of this new particle were consistent with those predicted for the Higgs boson. The scientific community erupted in celebration. It was a landmark achievement, a testament to human ingenuity and collaborative spirit. Peter Higgs himself was present at the announcement, visibly emotional. The discovery filled a critical gap in the standard model of particle physics and opened up new avenues for understanding the fundamental nature of our universe. The decades of searching, the immense investment, had paid off spectacularly. The discovery of the Higgs boson was not just about finding another particle. It was about validating the entire structure of the standard model. This model is our best description of the fundamental building blocks of matter and the forces that govern their interactions, excluding gravity. Before the Higgs discovery, the standard model was incredibly successful in explaining a vast array of experimental results. However, it had a glaring hole. It couldn't explain why fundamental particles have mass. The equations suggested they should all be massless, which is clearly contrary to observation. The Higgs mechanism provided the elegant solution, making the theory mathematically consistent and complete. Think of the standard model as an almost perfect instruction manual for the universe's subatomic world. It describes quarks, which make up protons and neutrons, and leptons, like electrons. It also details the force-carrying particles, photons for electromagnetism, gluons for the strong nuclear force, and W and Z bosons for the weak nuclear force. But without the Higgs field, the W and Z bosons would be massless, just like the photon. This would make the weak force have an infinite range similar to electromagnetism, which is not what we observe. The weak force is very short-ranged, and this is because its carriers, the W and Z bosons, are very heavy. The Higgs field gives them their mass. The Higgs boson itself is an excitation of this Higgs field. Its discovery confirmed that the field exists and that its interaction with other particles is indeed the source of their mass. It's like finally finding the architect who designed the keystone of a magnificent arch. The arch, the standard model, was mostly standing, but the keystone, the Higgs mechanism, was missing, and its absence made the entire structure feel precarious and incomplete. Finding the Higgs boson cemented the arch, making the standard model a far more robust and predictive theory. It's a cornerstone of modern physics, allowing us to understand why the universe has the structure it does. Moreover, the properties of the discovered Higgs boson, such as its mass, its spin, and how it interacts with other particles, are still being meticulously studied. These properties could offer clues to physics beyond the standard model. Are there more Higgs bosons? Does the Higgs field interact with dark matter or dark energy? Could it play a role in the very early universe, perhaps during the period of cosmic inflation? The Higgs boson isn't just an endpoint, it's a gateway. Its discovery confirmed what we thought we knew, but it also provided a new tool to probe the deeper mysteries of the cosmos, pushing the boundaries of our understanding even further. The idea of teleportation, instantly transporting people or objects from one place to another, has long been a staple of science fiction. Think of Star Trek and the iconic command, "Beam me up, Scotty," while human teleportation, as depicted in fiction, remains firmly in the realm of fantasy for now. The underlying concept isn't entirely without scientific basis, at least at the quantum level. Quantum teleportation is a real phenomenon, though it works quite differently from its fictional counterpart. It doesn't involve dematerializing an object and rematerializing it elsewhere. Instead, it's about transferring the quantum state of a particle to another particle, effectively creating a perfect replica at a distance. The process relies on a bizarre quantum phenomenon called entanglement. When two particles become entangled, their fates are linked, no matter how far apart they are. If you measure a property of one entangled particle, you instantly know the corresponding property of the other, even if it's light years away. To teleport the state of a particle, say particle A, you entangle another pair of particles B and C. Particle B is kept with particle A, while particle C is sent to the destination. A joint measurement is then performed on A and B. This measurement destroys the original state of A, but provides information that, when sent via classical means like a radio signal to the location of particle C, allows one to transform C into an exact replica of the original A. It's crucial to understand that no matter is physically transported in quantum teleportation. What's transferred is information, the precise quantum state. The original particle's state is destroyed in the process, so you're not moving the original atoms, you're recreating the object's quantum blueprint using atoms already present at the destination. This has been successfully demonstrated with photons, atoms, and even small molecules. However, scaling this up to a macroscopic object like a human being presents unimaginable challenges. The amount of information required to describe the quantum state of every single particle in the human body is astronomically vast, far beyond our current data storage and transmission capabilities. Furthermore, there's the Heisenberg uncertainty principle, which states that you cannot simultaneously know certain pairs of properties of a particle, like its exact position and momentum, with perfect accuracy. This poses a fundamental limit on how perfectly we can scan an object to teleport. While quantum teleportation cleverly sidesteps some of these direct measurement issues by transferring the state itself, the sheer complexity of capturing and transmitting complete quantum information comprising trillions upon trillions of atoms, each with its own intricate quantum state, remains a formidable, perhaps insurmountable, hurdle with current and foreseeable technology. Section 5. Cosmic tunnels, wormholes, and space-time shortcuts. Another fascinating concept often linked with advanced travel is the wormhole. A wormhole in theoretical physics is a hypothetical topological feature that could fundamentally create a shortcut through space-time. Imagine space-time not as a rigid, unchanging stage, but as a fabric that can be bent, stretched, and even torn and reconnected. A wormhole would be like a tunnel connecting two distant points in space, or even two different points in time, or perhaps even two different universes. Instead of traveling the long way across the fabric, you could dive into one end of the wormhole and emerge almost instantaneously at the other end, drastically reducing travel time. The idea of wormholes arises from Albert Einstein's theory of general relativity. This theory describes gravity not as a force, but as a curvature of space-time caused by mass and energy. The equations of general relativity allow for solutions that describe these tunnels. The first type of wormhole solution discovered was the Einstein-Rosen bridge, which connects a black hole to a hypothetical white hole, a region from which matter and light can only escape, not enter. However, these early wormhole models were found to be non-traversable. They would collapse too quickly for anything, even light, to pass through them, or they would require you to travel faster than light to cross them, which is forbidden. For a wormhole to be traversable, meaning something could actually pass through it, it would need to be held open by some kind of exotic matter. This isn't matter like the stuff that makes up stars, planets, or us. Exotic matter would have very strange properties, most notably negative mass-energy density. Normal matter has positive mass and pulls things together via gravity. Exotic matter, if it exists, would effectively have negative gravity. It would push space-time apart, propping open the throat of the wormhole and preventing it from collapsing. We have never observed exotic matter, and its existence is purely theoretical, though some quantum effects, like the Casimir effect, hint at the possibility of negative energy densities under specific conditions. So, while the mathematics of general relativity permits the existence of wormholes, actually finding or creating one is a colossal challenge. We would need to identify or create stable exotic matter in sufficient quantities. Then, we'd need to manipulate space-time with incredible precision to form the wormhole structure. Currently, wormholes remain firmly in the realm of theoretical speculation. They are fascinating mathematical constructs that push the boundaries of our understanding of gravity and space-time, but their practical realization is far beyond our present capabilities. They serve as powerful thought experiments, forcing us to consider the ultimate limits of physics and the nature of reality itself. Section 6. The Higgs connection, weaving wormholes into reality. Now, how does the Higgs boson, the particle responsible for mass, potentially connect to these mind-bending concepts like wormholes? The connection is not direct in the sense that the Higgs boson itself builds wormholes. However, understanding the Higgs field and its properties could be crucial for exploring the extreme physics required for wormholes to exist. The Higgs field is a fundamental scalar field, and its interaction with other particles gives them mass. The energy density of the vacuum, which is related to concepts like dark energy and the cosmological constant, is also linked to the properties of fundamental fields, including, potentially, the Higgs field. Some theoretical physicists speculate that at extremely high energies, perhaps conditions similar to the very early universe or near the singularity of a black hole, the behavior of the Higgs field could be different. Could manipulating the Higgs field, or understanding its deeper connections to space-time geometry, provide insights into generating the negative energy densities required for exotic matter? This is highly speculative. The standard model, even with the Higgs boson, doesn't predict exotic matter or provide a clear pathway to creating traversable wormholes. However, physics beyond the standard model, which the Higgs boson might be a window into, could hold some answers. The energy scales involved in potentially creating or stabilizing a wormhole are thought to be immense, possibly near the Planck scale, where quantum gravity effects dominate. The Higgs field's vacuum expectation value, its non-zero value even in empty space, plays a crucial role in setting the scale for particle masses. If this vacuum energy could be manipulated, or if other yet undiscovered scalar fields exist with specific properties, they might contribute to the kind of negative pressure or energy density needed to support a wormhole. This line of inquiry pushes physics into uncharted territory, blending particle physics with general relativity in ways we are only beginning to explore. It's important to reiterate that this is at the very edge of theoretical physics. There's no established theory directly using the Higgs boson to create wormholes. However, the discovery of the Higgs boson completed the standard model and, in doing so, also highlighted what the standard model doesn't explain, such as dark matter, dark energy, and a quantum theory of gravity. As we study the Higgs boson's properties with greater precision, we look for deviations from standard model predictions. Such deviations could point towards new physics, new particles, and new forces, some of which might, just might, have implications for the stability of exotic space-time structures like wormholes, or even the nature of teleportation on a grander scale. Section 7. Beyond imagination applications of instant travel. If we could somehow harness teleportation or stable wormhole travel, the implications for humanity would be staggering, transforming civilization in ways we can barely comprehend. Imagine instantaneous travel to any point on Earth. The concept of distance would become almost meaningless for transport. Commuting to work could mean stepping into a teleporter in your home and appearing in your office, even if it's on another continent. International trade could be revolutionized, with goods teleported instantly, eliminating shipping times and costs. Emergency response could be immediate. Medical teams or disaster relief could arrive at a crisis zone in seconds, saving countless lives. Consider space exploration. Reaching Mars currently takes months. With advanced teleportation or a conveniently located wormhole, astronauts could travel to Mars, other planets in our solar system, or even exoplanets orbiting distant stars in a fraction of the time or perhaps instantaneously. This would open up the cosmos for exploration and potential colonization on an unprecedented scale. We could establish research outposts, mine resources from asteroids, and search for life beyond Earth with an ease that is currently pure science fiction. The universe would truly become our backyard. The challenges of long-duration space travel, like radiation exposure and psychological strain, would be greatly mitigated. However, such powerful technology would also bring profound societal changes and potential challenges. Economies built on traditional transportation industries, shipping, airlines, trucking, would face massive disruption. The geopolitical landscape could be reshaped. If one nation or entity controlled this technology, it could wield immense power. Access would become a critical issue. Would this technology be available to everyone, or only a select few? The potential for misuse, such as instantaneous military deployment or untraceable smuggling, would also need to be carefully considered and regulated. The very structure of our cities and societies might change as geographical proximity becomes less important. Beyond these practical considerations, the ability to instantly traverse vast distances could fundamentally alter our perspective on our place in the universe. If we could easily visit other worlds, or if wormholes provided glimpses into other regions of space-time, our understanding of reality itself would expand. It could foster a greater sense of global and even galactic community. The resource limitations of a single planet might become less pressing if we could access the resources of the solar system or beyond. The dream of becoming a multiplanetary species would be within reach, securing humanity's long-term survival against terrestrial catastrophes. Section 8. New Worlds, New Rules, the Ethics of Crossing Dimensions. The prospect of interdimensional travel, perhaps facilitated by hypothetical advanced wormholes connecting to other universes or dimensions, raises even deeper philosophical and ethical questions than simple teleportation within our own space-time. If we could truly access other dimensions, what responsibilities would we have? Would these dimensions be empty, or could they harbor life, perhaps even intelligent civilizations? The prime directive, often seen in science fiction, the principle of non-interference with less developed civilizations, would become a paramount ethical consideration. How could we ensure our arrival wouldn't cause irreparable harm, culturally or biologically? What if these other dimensions operate under different physical laws? Could travel to such a place even be safe for us? Or could we inadvertently cause damage to that dimension's fabric of reality? The very act of opening a gateway between dimensions could have unforeseen and potentially catastrophic consequences for both our universe and the one we connect to. There's the contamination issue, both biological, us carrying microbes to a new ecosystem, or vice versa, and existential. What if ideas or technologies from one dimension could destabilize another? The ethical framework for such exploration would need to be incredibly robust and universally agreed upon, which is a monumental challenge in itself. Furthermore, the philosophical implications for humanity's understanding of itself would be profound. If we discover we are not unique, or that our universe is just one of many, it could reshape our religions, our philosophies, and our sense of purpose. What if other dimensions hold beings far more advanced or powerful than us? The power dynamics would be incredibly complex. There's also the question of resource exploitation. If another dimension is rich in resources we desire, what right would we have to take them, especially if it's uninhabited but cosmically significant in other ways? The potential for conflict or misunderstanding would be immense. Ultimately, the ethics of interdimensional travel would force us to confront fundamental questions about our values as a species. Are we explorers or conquerors? Are we seeking knowledge or dominion? The temptation to meddle, to use such technology for selfish gain, or to escape problems in our own dimension rather than solving them, would be strong. Establishing clear ethical guidelines before such technology becomes a reality, if it ever does, would be crucial. It would require a global, perhaps even multi-universal consensus on principles of respect, caution, and the preservation of cosmic diversity. The responsibility would be immense, as our actions could have consequences on a scale far beyond our own world. Section 9. The Universe Awaits, Humanity's Next Frontier. The journey from theorizing about the Higgs boson to its discovery was a triumph of human intellect and collaboration. It solidified our understanding of how the universe gets its substance, completing the Standard Model. While the God particle itself doesn't directly offer us teleportation pads or stable wormholes today, The relentless pursuit of fundamental knowledge it represents is precisely what fuels our dreams of such future technologies. Understanding the deepest laws of physics, including the nature of mass, energy, space-time, and quantum mechanics, is the first essential step towards potentially manipulating them in ways that now seem like magic. Teleportation, at least in its quantum form, is already a reality in laboratories, albeit on a microscopic scale. Scaling this up to macroscopic objects, let alone humans, presents formidable, perhaps insurmountable, challenges related to information, complexity, and quantum coherence. Wormholes remain even more theoretical, depending on the existence of exotic matter with negative energy density, something we've never observed. Yet the equations of general relativity allow for their possibility, tantalizing us with the prospect of cosmic shortcuts. The continued study of the Higgs field, dark energy, and quantum gravity may yet reveal new physics that could change our understanding of what's possible. The potential impact of mastering such technologies is almost beyond our capacity to fully imagine. Instantaneous travel could dissolve borders, revolutionize economies, and open the entire cosmos to human exploration. It could transform us into a truly spacefaring, multiplanetary species. However, with such immense power comes immense responsibility. The ethical and philosophical dilemmas raised by teleportation and interdimensional travel would require profound wisdom and foresight. We would need to navigate questions of access, control, non-interference, and the very definition of what it means to be human in a potentially much larger, more complex reality. For now, the Higgs boson serves as a reminder of how much we've learned and how much more there is to discover. Each fundamental particle found, each cosmic mystery unraveled, brings us a tiny step closer to understanding the ultimate rules of the universe. Whether these rules will one day permit us to beam up or traverse cosmic tunnels remains to be seen. But the quest for knowledge, driven by curiosity and the unyielding human spirit of exploration, will continue. The universe is vast and full of wonders, and the pursuit of understanding its deepest secrets is humanity's grandest adventure, potentially unlocking futures we can currently only dream of.